Hello, this is Mr. Craig, and this is quiz number 2 for period number 1. Alright, let's go ahead and get started here. Question number 1 through 4 states that the set of lettered choices below is a list of electron configurations. Select one of the lettered choices that best fits each statement. Choice may be used once, more than once, or not at all. Number 1, it says an impossible electron configuration. Alright. When we look at the periodic table, we have to know what's going on the periodic table for designating our orbitals. Do realize that the first two columns, represent your s orbitals. The last 6 columns over here represent your p orbitals. These columns here in the middle, starting with scandium and ending with zinc on down, those are your d orbitals. And then your f orbitals are down here, the bottom 2 rows. Okay, so there we have our f orbitals. So knowing that, and then just like whenever we do electron configurations, we always start with hydrogen, then we drop electrons in each box. What I want you to notice is in the first energy level, or first row, because with the s orbitals and the p orbitals, the energy level is the same as the row that it occupies. Okay, so s and p are the same row that the energy levels in. The d orbitals actually are one less than the row they're in. Notice that the d's actually begin in the 4th row, but it's the 3rd energy level. And then the f orbitals are actually 2 rows behind, and they start right around here, right after barium, and they go here. Okay, so that's our background. Again, just a nice little refresher. So when we look at where where orbitals begin, s orbital begins in the first energy level, okay, or the first row. So when we look at the periodic table, the only thing that we have in the first row are 2 boxes, which represents 1 electron for each box, which represents the first s orbital. Excuse me. And then looking at the p orbitals, that begins in the 2nd row. Looking again at the periodic table, the p orbitals are over here, which start in the 2nd row. Okay. D orbitals begin in the 3rd energy level, or 3rd row. I'm sorry, 3rd energy level, which in this case is actually the 4th row. And the f orbitals begin in the 4th energy level, which is actually the 6th row. Okay, that's nice to know where these things are actually being introduced. So when we look at this, looking at our choices, I see that we have a 2d orbital. In the 2nd energy level, we have s and p. We do not have any d's because d's are introduced in the 3rd energy level. Okay, so for number 1, C is the best answer. All right. Number 2, the ground state configuration for the atoms of a transition element. Again, transition elements are right in this area here, so it's the drop down. So we're looking for something with a D orientation. So when we come back here, we have 3s, 3p, no. 3s, 3p, no. That one's illegal to begin with, so don't pick it. Here we have an option. Yep, looks like we only have 1. So D would be our best choice. D as in dog. Okay. The ground state electron configuration of a negative ion of a halogen. Okay. Well, find it in the periodic table. Make sure you know what the columns represent. The first column is your alkali metals. Your second column is your alkali earth metals. And then jumping all the way over here to the fluorines column, that's your halogens, all the way down, group 7A. And then noble gases are our last column. So again, just because nitrogen, oxygen, fluorine, and chlorine are gases, they are not noble. Noble means that they're in this last column and they have a full s and p orbital. All right, so the question wants to know the configuration of a negative ion of a halogen. Well, I hate to tell you guys, but this answer could actually be for a halogen, or for oxygen, or any element in the s orbital. I'm sorry, the oxygen's column, which has no specific name, nitrogen's column, because what we're looking at, if we're looking at a halogen, what charge should it have? Hopefully you said -1. which means it has the same electron configuration as the nearest noble gas. Well, that's the electron configuration for everything in that row that has a charge. So really, this answer doesn't really need for it to say of a halogen. It just needs to say ground state electron configuration of a negative ion, period. Okay, but let's make sure that we have our S and P orbital completely filled. Okay, no, we already said that was a transition. That one's looking pretty good. I'm sorry, it's not looking good because that 2D. But this one right here, B, we have 8 electrons represented there. So for a negative ion, okay, that's our best choice. So letter B for number 3. All right, number 4, the ground state configuration of a common ion of an alkali earth metal. What did I just say? It is isoelectronic for an element, or I'm sorry, for an ion to have a charge. It'll have the same electron configuration as its nearest noble gas. So when we look at the elements that are in group 2A, or alkali earth metals, these will all have the same electron configuration as its nearest noble gas. So if I'm looking at calcium, and I lose 2 electrons, because that's its most common charge, all the elements in second column will have a +2 charge. It will have the same electron configuration as argon. Okay, so what we're looking for is an electron configuration of a noble gas. Guess what, guys? We get to use an answer more than once. So we're going to use B as in boy again because it has 8 electrons. So because it has the 8 electrons, this is isoelectronic for everything, pretty much in the 3rd row, and the metals in the 4th row. Okay. And again, I'm talking about representative elements. Now, what are representative elements? Representative elements are any of the elements that lie in the S columns or the P columns. Those are your representative elements. So, transition metals, not representative. Intertransition, these are the F orbitals. Intertransition, not representative. Okay? Make sure that you know what representative elements are. All right, I think we're done with number 4. Okay? Number 5. It says the weight of sulfuric acid, H2SO4, has a molecular weight of 98.1 grams. Okay, it's given to you. In 50 milliliters of a 6 molar solution, we're looking for the mass of this. So again, since we have, 50 milliliters, and again, we can do this real quickly. 50 milliliters, you don't need a calculator. Convert that to liters, and if you need to, you can do it like this. Okay, so that's how many we have. So if we know our volume and molarity, always start with your volume, and then we have our 6 molar, which is moles per liter. Okay, and then it wants to know the weight. Well, in 1 mole, we have 98 grams, essentially 100. So be smart about it. 100 grams. Okay, so 1 mole of H2SO4. Okay, so we have 0.5 times 6, which is equivalent to about 0.3, and then times 100. So hopefully C, just by guesstimating there. Okay, now again, notice what I did. If I'm worried about 98.1 grams there, I'm going to be working on this for quite a while. So I have to use quick mental math on that. Number 6 says a gaseous mixture containing 7 moles of nitrogen, 2.5 moles of oxygen, half a mole of helium exerts a total pressure of 0.9 atmospheres. What is the partial pressure of nitrogen? All right, now remember gas laws. That if we have 1 mole of any gas, and we'll assume that's a STP. It doesn't tell us what it is. A 1 mole of any gas has a volume of 22.4 liters. So whatever the pressure is for this, whatever the temperature is for this, all these gases are behaving in the same way. So we can treat them all as equals. So what we need to do is find out how many moles we actually have of gas. So we have 7 moles of nitrogen, 2.5 moles of oxygen, 1/2 mole of oxygen, which is 10. Okay, so since the total pressure, PT, equals 0.9 atmospheres, we need to find out what the partial pressure due to nitrogen is. Well, we have 10 parts, which means that we have 10 moles here, which 10 even parts. And if we say that, okay, each one of these parts, or I'm sorry, all 10 of these parts has a total pressure of 0.9, what does each part weigh or exert what pressure? So we actually have 7/10 of 0.9 atmospheres. And again, don't write units. This is multiple choice. So whatever 7 times 9 is. So actually it's, 0.7 times 0.9. So I believe that is 0.63, somewhere around there. So the best choice in this case would be C. Now, let's be logical about this. Did I really even have to do that type of calculation? I think we can honestly, here, let me erase that answer there. I think we can honestly eliminate that 0.9 is not going to be an option. I think we can also eliminate 6.3 atmospheres as an option. There's no way that if the total pressure is 0.9, that it's going to be 6.3. You can't do that. Also, we know that if this thing is mostly nitrogen, it can't be 0.13. Also, a third of that would be about that. So technically, I didn't even have to do a calculation. But look for the things that you can automatically eliminate before you start doing any calculations, because if you eliminate a couple of them, the obvious answer may jump out at you, and you won't even have to do a calculation. But if you have time, circle it and come back. Okay? That's our strategy. We're going to circle things and come back to them. All right. Number 7, the Lewis dot structure of which of the following molecules shows only one unpaired or unshared lone. The Lewis dot structure of which of the following molecules shows only one unshared pair of valence electrons. All right. So looking at chlorine, if you need to draw it real quick. Okay, well, we have a bunch of unpaired. I can stop right there. That one's out. Looking at nitrogen, I know it has a triple bond. Lone pair, that one's out. Looking at water, hopefully we have water memorized by now, where we have 2 lone pairs. That one's out. Looking at carbon tetrachloride, well, we have chlorines all the way around this thing. Okay, so that one's out. So that should be our answer. And honestly, it is, because we have 3 hydrogens and 1 lone pair. Okay, so again, be quick on doing this. And some of these structures you really should have memorized if you've used them enough. Water, that's one that should be somewhere up in your memory bank. Nitrogen, hopefully you're recognizing, okay, nitrogen each brings 5 electrons, so a total of 10. I know there's a triple bond in there because it's a group 5A. It's 3 away from the noble gases. So according to formal charges, nitrogen needs to have a triple bond. Therefore, that occupies 6 of those electrons. 4 of the others are not being shared. Boom, 2 pairs. Chlorine, we know based on formal charges, it's in group 7A, 1 away from the noble gases, which means that it will have a single bond. And chlorine each brings 7 electrons. Multiply that by 2. So that means that 2 of those electrons are shared, while the other 12 are not being shared. So things like that you have to be able to process quickly. And again, this is all about problem solving. All right, so 7 should be E. Number 8, a compound that contains 29.6% of oxygen is, well, you know you can't do that one. And again, roughly speaking, sulfur is around 32 grams per mole, oxygen 16 grams. Okay, talking about elements here. So if I have 3 of these, I know I have more oxygen. So I'm looking for about a third of the mass to be oxygen. Nope. Again, way too much. That's all we have. That one's looking pretty good. We have 16 and 38. That one I'm kind of liking. That one's out. Yep. D. Okay. I'm not going to do an actual calculation to see if it's 29.6. This is a sprint, guys. Do not work these problems out to get exact percents. You would be wasting your time. All right, number 9. When the equation for the half reaction above is balanced with the lowest whole number coefficients for the electrons is, okay, I'm going to do it in the step or in the order that you would do a redox equation. Step 1, balance the non-hydrogen, non-oxygens first. So we have 2 chromiums. We need a 2 there. Okay. Now we're going to balance out the number of oxygens. So I have 7 oxygens on this side. How do I do it? I add water. So I need 7 on this side. Then I balance the hydrogens. So I have 14 hydrogens, so I need a 14 there. Now I have all of my atoms balanced on both sides. Again, the order is non-oxygen, non-hydrogen elements get balanced first. Then oxygen atoms get balanced next by adding water molecules. Then we balance the hydrogens from the water that was given here. Then the last thing is, what we haven't done yet, is we need to balance the charges. So we have to find out what the total charges are. Again, we have a 2 here, and there's a +3, so that's a total of a +6 charge on the right-hand side. We have a -2 over here, +14, so that is a +12. So I need to get the charge to be +6, so I need to add 6 electrons. C is in cat. Redox. Make sure that you're understanding that. You will see at least 2, if not 3, redox type equations. I promise. Alright, number 10. The mass of element Q, not one of our elements, so don't go looking on the periodic table, found in 1 mole of each of the 4 different compounds is 38 grams, 57 grams, 76 grams, and 114 grams respectively. A possible weight, atomic weight for Q is, alright, make sure that we read the question carefully. It says that Q is found in 4 different compounds. So that means Q is with something else. Okay? It's got to be with something else. So, is E an option? Absolutely not, because there's no way Q could weigh 57 grams if we have it in a compound that makes up 38 grams. Is it possible for Q to weigh 38 grams? No way, because if Q weighed 38, then X would weigh nothing. That one's out. Alright, so now we have to find something that is divisible by what these values are increasing by. So 57 minus 38, what is that, 19? I think so. Sorry about that. 17 and, yep. So 19. 19's looking pretty darn good here. So we increased it by 19, so it can't be by a factor of 27. So now we're down to A and B. My choice is 19, because we increased it by that amount. So it looks like we might have like a Q2 X2 for this, and we increased it and made it like Q3 X3. Okay? Not 12.7. There's no way it could be 12.7. Why could it not be 12.7? Think about it. If I had, say, well, 38, is there any way I could get 38 into that? Yeah, I can get it in there 4 times, but what about 6 times? No. So that 0.7 makes it very, very difficult to get a whole number. So 19 is our best option. Okay. Number 11. At STP, what is the maximum number of liters that oxygen can react with methane to form 6 liters of water? All right. Well, let's... Whoa, easy. All right, so we have to write a balanced equation. So we have methane, CH4, plus water, plus carbon dioxide and water. Got to know this. You're going to see this in question number 4, I promise. Or something like this, a combustion reaction. You will be asked to do some reactions in question number 4. All right, so we've got 2 there. Ooh, sorry about that. We don't want water there. We want oxygen. My bad. It's like, what is that? So O2. All right, so we've got 4, 1, so I've got 2, so we need 2 there. Okay? All right, so we've got our equation balanced, and it wants to know at STP the maximum number of liters of oxygen can react with methane to make 6 liters of water. So we have 6 liters, and we're looking for the maximum number of oxygen. Now again, notice what I'm doing here. I'm using up a lot of time. This definitely would be one that I would circle and come back to. But since we're doing it, let's finish. So we start off with what we know. Oops. 6 liters. Let me move up just a hair here. So 6 liters of water. So that means in 1 mole of water, we have 22.4 liters. Okay. Use your mole ratio, water, and we're looking for 2 moles of oxygen, and it wants to know what is the number of liters. So go one more step, 1 mole. Again, 1 mole of any gas at STP is 22.4. All right, let's start canceling. So 22.4s can cancel, 2 can cancel. 6 liters should be our answer, E. Okay. Whoa. What? What'd I do there? What'd I mess up on, guys? 6 liters. Did I bounce that right? 2, 2. Huh. Alright, hang on here. 6 liters. Did I read this right? 6 liters of water. I think I'm good here. If I said C on the quiz, I might owe some of you some points here. Because that is balanced. Yeah. I bet 4 hydrogen, carbon. Yeah, the right answer should be E on this. I may have to look at some of your quizzes, guys. That's E. That's not C. Alright, sorry about that. Alright. Number 12. Rank the following with respect to increasing bond angle, large to small. Alright. Make sure we can draw Lewis structures for these. So SO2. Well, we're going to have a double bond on one of these, a single bond on another, and a lone pair. So since this forms a trigonal planar shape, we have 120 degrees. Looking at the water, we have something very similar. That kind of looks similar, except there we have lone pairs of electrons, and this is a tetrahedral shape with 109. Carbon dioxide, will have double bonded oxygens, no lone pairs, so this is a linear shape with a 180 degrees. And SF6 will have 6 fluorines all the way around, and this is an octahedral shape at 90. Alright, so increasing bond angle, small to large, so it's going to be 4, 2, 1, 3, which is A. Okay. Yeah, and then I gave those angles. And make sure that you know what these shapes are. The bent. Notice that the bents don't always equal the same angle because, again, trigonal planar and tetrahedral. The linear is 180 always, well, unless it's a trigonal bipyramidal shape, and then you have 120 and 90. So be careful with that. Octahedral, 90. All right, number 13. A compound contains 1.1 mole of potassium, 0.55 moles of selenium, 1.65 moles of oxygen. What is the simplest? That looks like a 0. I need to change that to an O. What is the simplest formula for this compound? Well, let's look at if we're doing empirical formulas, this is our smallest value, so that's a 1, that's a 2, and that's a 3. So whatever our ratio is, so K2TeO3. There it is. B. Okay. Again, not one of our polyatomics, but again, empirical formulas without a calculator. Big fun. Alrighty. Of the following compounds, which is most ionic? Alright, looking at a periodic table, when we determine ionic nature, the farther they are away from each other, the more ionic. Actually, more polar as well. However, if we look at, say, charge-wise, if we're looking at, say, like oxygen and magnesium, that might be a little more ionic because of the charge status. So it depends on, and again, let's take a look at our options. We want to pick the best one. SiCl4, that's over here, silicon and chlorine. It's not looking too good. Bromine and chlorine, they're on top of each other. PCl3, that's right next to each other. PCl, yep, I'm not finding anything yet. ClO, so oxygen, no. And hey, there's one. It's actually our only ionic compound, so E. Most ionic, the only one listed. All right. What set of quantum numbers is impossible? Yeah, this is a good discussion here. All right. When we talk about principal quantum numbers, make sure we know what each one of these rows represents before I even answer the question. Okay. The first row, N. Or I'm sorry, first column, N. N equals the energy level. And N will start at 1 and theoretically go on for a long time. So typically we'll say maybe not more than 20. But it technically could go on for infinity. But we won't say that. Okay, so N represents the energy level, the size of the orbital. Yeah, let's just leave it at that. The second value is L. I'm sorry, not L, but darn it. Not L, but M sub, no, it is L. Yeah. It is L. Come on, get back. It's L. L. And L represents the type of orbital. So we want to go from N minus 1 through 0. And what's really important here is these numbers actually mean something. So if L equals 0, you're looking at an s orbital. If L equals 1, you're looking at a p orbital. You're looking at 2d, 3f. Know that. You're going to be asked, what orbital is that electron residing in if we're looking at, say, that number right there. Now, 4 is given here, but you won't be asked for it. It's a g orbital. Okay, so this one's just asking which one is impossible. So make sure we know those. Okay, so, excuse me. And then our next row, next column is M sub L, which represents orientation. And orientation goes from L through 0 through negative L. Or you could write it opposite, negative L through 0 through L. That's fine. Now, do realize that if I have an s orbital, okay, again, I'm looking at my L. If I have an s orbital, which is equal to 0, my L is only 0. Okay, so I only have 0. If my L is equal to 1, then I will go 1, 0, negative 1. Okay? Now, think about this. What does 1 represent? P orbitals. How many p orbitals are there in any given energy level? 3. How many s orbitals are there in any given energy level? 1. If I have a d orbital, my orbitals go from 2 to 1 to 0 to negative 1 to negative 2. How many orbitals are there in the d orbitals? 5. Okay? I think you get it. All right. And then the last one, M sub S, is your spin. So positive or negative. The last, that's garbage, that's garbage. All right, so what we need to focus on is making sure that it follows the criteria that we just had. So 5, 4, 3, that sounds good. 3, 4, 5, not looking pretty. 5, 4, negative 3, yes. 3, 0, 0, absolutely. 4, 3, 1, yes. Now, B is the one that is impossible. Let me say that I rewrite this one. Let's say that we have 3, 0, negative 1, plus 1/2. Okay? Is that a legal set of quantum numbers? Hopefully you said no. The reason being is this is an s orbital, and it only has an orientation of 0. Okay? Again, make sure you know what that number right there means. It represents a type of orbital, and if it doesn't fall between L, this is L, this value here doesn't fall between L, 0, and negative L, it's not legal. Okay, so it doesn't have to just be bigger than the number in front of it. Oftentimes that's the case, But if I had 3, 0, 1, that's wrong. Can't have it. All right, 16. The noble gases are highly reactive with many elements. Negative. Helium, no. Not lithium. Highly acidic, no. That would mean it would be reactive. Helium, neon, argon, no. Therefore, it has to be this. So non-reactive with many elements. True. Again, noble gases only reside right here in the far right column. Okay? All right. Number 17. Which of the following correctly lists the electromagnetic radiation in decreasing order of energy? Now, I'm not telling you that you have to memorize light, but it's nice to know. Okay? Radio waves is a form of light. Radio waves have the biggest wavelength. Big honking wavelength. Some of these things are almost like 10 kilometers in length. Very low energy. So if we have a big wavelength, that means we have low energy. So radio waves, and then there's a few others there. I can't remember what goes right after that. But right before Roy G. Biv, and everybody should know Roy G. Biv. Okay? Right before Roy G. Biv, on the red end of the spectrum, you have infrared, which is... Oh, I didn't mean to do that. On the red end of the spectrum, we have... come on back. Hang on here. Sorry, guys. Okay. We have, right before red, we have infrared. Okay, so we have infrared. That is low energy light. Yeah, it'll burn you if you're exposed to it enough. Big difference. Exposure time. You're going to get burnt by any kind of light. And then the Biv here, the violet, ultraviolet, goes on this end. Okay, now, Roy G. Biv, low energy, is on the red end of the spectrum. High energy is on the blue end or violet end of the spectrum. When you get into astronomy, pretty cool stuff. If you see a red giant star, like Betelgeuse, that's a low energy. It's a giant, but it has a low energy. In other words, it's a cool star. In other words, the temperature isn't as hot. Now, I wouldn't want to go there. I'd get fried, but it's a low energy star. There are stars that have blue light. Yes, actually they have blue light. That's very high energy. Okay. Some of them even have X-rays and gamma rays. That's even higher energy. That's all form of light. So radio, the ultraviolet, X-rays, all that jazz. Okay, so I've got a generic thing here. Highest energy first, so we're looking from this way going that way. Definitely high. Microwaves actually fall right before infrared. So microwaves are right before infrared. So boom, boom. No, because the ultraviolet should be in front of there, so C's out. Micro, we're going highest, no. Infrared, no. Ultraviolet, visible. Yeah, there we go. A. Visible, ultra, nope. Okay. And again, how much time and energy are you willing to put in to memorize the light is up to you. Make sure the rain's not coming in. Sorry guys, I'm at home here and the windows are open and it's starting to storm. Yay. Alright. Alright. Number 18. Balance the half reaction for an acidic solution using the smallest whole number coefficients. So again, let me get my... I won't be able to. Alright. Excuse me. So the first thing, again, just like what we did in the other redox equation, was, balance the non-hydrogen, non-oxygen elements first. Our vanadiums, 1 to 1, we're good to go. Number 2, we need to balance the oxygens with water molecules. So we have 3 oxygen there, so we need 3 waters. And then we need to balance the hydrogen, so we have 6 hydrogen, and use hydrogen ions since we have an acidic solution. We have a total of a plus 3 charge on this side, a plus 5, so I need 2 electrons. So then, now that I'm balanced, it should be D, 2 on the left. Okay, I like redox. You guys, redox is pretty easy. I hope you like redox as well. Alright, Number 19. Oh, we're almost done here. If 20 milliliters of a 0.1 molar solution of silver nitrate is added to 80 milliliters of a 0.1 molar solution of calcium chloride, what is the final concentration of chlorine ions in the solution? Okay. This definitely is a time consumer. This would be a circle if it were actually number 19 in the 75 questions. Something you could probably do without a calculator. A lot of you could probably, I honestly believe, could do it without a calculator. So I would skip this and come back. However, since you've already answered all the other questions and you have 10 minutes left, now's the time to just sit back, relax, and answer this question. So we know the volume and the molarity for our silver nitrate. So I'm going to change that to liters. And I hope you can do that in your head. So if you know the volume and the molarity, start with the volume. And then in 0.1 mole of silver nitrate. And we're looking for the final chlorine concentration. So we're looking for actually the limiting. No, here, let's do this. Sorry. Silver nitrate. This is a stoichiometry problem. Sorry, guys. Got to read the question. Okay, so we're going to make some silver chloride, which is a precipitate, and some calcium nitrate, which does absolutely nothing. Soluble. Okay, so we'll put a 2 in front of there, a 2 in front of there. Okay. So balancing this out, we have 1 mole silver nitrate. We don't want that there. Okay. So we're doing a limiting reactant. So we have 0.1 of that, and I want to know how much of the calcium chloride. So it's a 2 mole to 1 mole ratio. Now, the 2 moles is the silver nitrate down here. Calcium chloride is right here. I'm trying to save time here. And then I want to convert back into milliliters. So I have a 0.1 molar solution of calcium chloride. Okay, 0.1 molar. And then go back to liters. Okay. All right, so we know that that can cancel out. We actually have 0.2 divided by 2. So that means that we have 10 milliliters, I believe. We'll use 10 milliliters of the calcium chloride. Okay. So our silver nitrate is our limiting reactant, which we would expect since we only have 20 milliliters and we have the same concentration. Now, the reason why I wanted to do this calculation was to find out how much of this we were going to use. Because if we look at the calcium chloride, it wants to know what is the final chlorine solution. Well, all the chlorines here get used up. Okay, they're no longer ions. They're all by themselves. So what this means is we actually have 70 milliliters of calcium chloride remaining. Okay, so what that means is I need to find out, okay, how many chlorine ions does that actually mean? So I'm going to take that, change it into liters. Hope I didn't write too big. I'm going to multiply that times the molarity. So again, 0.1 moles of the calcium chloride per liter. Now here's the difference. In 1 mole of calcium chloride, I have 2 moles of chlorine. Now I want to stop right there because I need to know how many moles of the substance I have. Okay, so I actually have 0.07 times 0.1 times 2. Okay, so I have so times 0.2, and so that is 0.014 moles, I believe. I'm trying to do this math in my head here. Yeah, that's right. Do this real quick because I'm stupid. Okay. So 4, 1, and should have a 0. So there's my number of moles of chlorine ions. Okay, let me erase some of this. Okay. So I have erase. Come on, erase. 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 Really? Honestly, you don't want to erase. Okay. All right. Now that I have my number of moles, 0.014 moles of chlorine, what is my total volume? 20 plus 80.1 liter. So I should have a 0.1 molar. Hopefully see. And again, that did take quite a bit of time. Okay. And there is the steps that I, in a cleaner fashion, holy cow. Sorry about the chicken scratch. But again, this is not something that you're going to do in 30 seconds. This would take more than 1.2 minutes to solve. But again, it is a stoichiometry problem. It is a question that you could do, and it looks like I may have tried a couple other methods as well. I don't know why I did this equation right here, but that's interesting. But I needed to find out how many moles of chlorine ions were remaining and then find the concentration. Okay? Again, not something I would do early on in the AP exam. This would be a question I would circle, and yes, they would give you something like this, so don't freak out here. Number 2, an unknown liquid reacts violently with solid sodium hydroxide and shows a white precipitate when treated with a solution of barium chlorate, perchlorate. The unknown is most likely. Okay, this is a precipitate type question. So the thing that we have to look at is what will form here. Don't get all hung up over that. That doesn't tell us anything. All right, plus NaOH. Okay. Now, even though that's one of our polyatomics, actually we do have perchlorate. Or we know we have chlorate, but it's going to behave the same way because we have sodium. And what does sodium do with anybody? Nothing. However, the barium, when it hooks up with the hydroxide, okay, the barium hydroxide likes to form a nice little white precipitate. Okay, so when looking at, oh, I'm sorry, back on it. That's not what we want. Okay. That's not what's happening. That's actually what is formed at the end. Okay. Okay. All right, sorry. Let me restart this over because barium on down is good. All right, so we're going to treat this barium chlorate with something here. Okay, so the barium hydroxide is soluble. So this doesn't form a precipitate when we put the sodium hydroxide with the barium perchlorate. However, when the barium chlorate reacts with one of these things, we need to find out who forms a precipitate. Well, nitrate, no. Sulfate, cold beer, Pizza Hut. Okay, sulfate's looking pretty suspect there. Absolutely not. Nobody knows what that is. And carbon tetrachloride, no. So, according to solubility rules, this forms a precipitate. Okay. And again, when we talk about sulfate, all sulfates are soluble except with cold beer and Pizza Hut. Now again, the cold beer is calcium, barium, and the Pizza Hut is lead, mercury. Okay. Solubility rules. Love them, learn them, enjoy. All right. Whew, that was a little long-winded. I apologize. I need to take a look at that one question again with the methane. Yeah, I need to fix that. That is not letter C. That should be letter E. All right, I'll double check that with some of your quizzes. You guys may be getting a point or two. I hope this video's helped. If you have any questions, don't hesitate to email me.